Now, I want to talk about the linear least squares problem. What does the linear least square problem mean? Well, for example, I have some t and some b, whatever that is. This is the x coordinate, and let's say this is the y coordinate, right? And I have a model which I think does this, which I think models some relation, that is, takes the input as ti and gives the output as bi. This is what I think as a model. Now that model has some parameters. Not only does it depend on ti, but it also depends on some parameters, x1, x2, x3, up to, let's say, xn. This is my complete description of the model. It depends on some x1, x2, x3 up to xn, and also takes the input as ti, and this I propose give the output as bi. Now why is it called the linear least squares problem? It's called the linear least squares problem because the model parameters enter linearly. For example, if I write phi as t square x1 plus t cube x2 plus square root t x3 versus if I write t x square x1 square plus t square x2 cube plus t e to the power t e to the power x3. This is a linear model because all of the model parameters enter linearly. This, however, is a non-linear model. So we right now are only going to focus on the linear part, right? We will not focus on the non-linear part. So the problem is, the question that I want to answer, is, can I find x such that this error is minimized? Sigma find x such that this error is minimized. This is the squared error, and that's why this problem is called linear least squared problem. I want to find x such that this error is minimized, right? Now I will formulate and I will write I can always write the reason I was so specific about it being a linear problem is because I can write my phi of x as ax equals to b, where x are all of those model parameters entering linearly. A is just another coefficient matrix which depends on the values of t which are in the coefficient of x, and this is it, ax equals to b. This is what my phi of x is, right? And what I want to do is find the minimum of this, b minus ax norm square. This is the 2 norm, right? This is the 2 norm. 2 norm is square each individual element and add them together, and this is the square of this. This is what I want to minimize. Minimize b minus ax norm squared with respect to the 2 norm, and I want to find x such that this error is minimized. I write it as phi of x. This is what my problem definition is. That's why I wanted it to be linear, so that I can write it as b minus ax. So how do we find an x which minimizes this problem? Well, let's differentiate and put it to 0. let's take the derivative of phi of x and put it to 0. I can write the norm as b minus ax transpose times b minus ax, and I want to differentiate this. I want to take the gradient with respect to x of this entire function, this entire thing. How do we do it? Keep this on this side and differentiate with this, then keep that aside and keep differentiate with that, right? So let me just skip a few steps and write the result directly. Write the result of the derivative. Put the derivative with respect to this equals to 0, skipping a few steps, comes out to this: A transpose A x is equals to A transpose B. This is known as the normal equation. An x which satisfies this will solve that problem, minimization of B minus AX, right? A transpose AX is equals to A transpose B. And x which satisfies this, so that x becomes A transpose A inverse B. So given such an A and given a B, this is what my answer is: A transpose A inverse A transpose B. A transpose B. Okay? Now, well, obviously we will never directly implement that because we never do inverse, and we also never do A transpose A. Why? We'll look at it in a minute. Why do we never do A transpose A? But before that, I want to give a geometric perspective to this. I want to give a geometric perspective to the entire problem. Let's say this is my high dimensional space, n dimensional space, and this is my hyperplane, which is like the span of A. So basically this is AX for all x. This hyperplane gives me AX for all possible x, and this is my B. Let's say this is my B. Now I want to find an x, let's say an x here, such that the norm of B minus AX is minimum. I don't think it is a big thing for you to understand that such an x will be an orthogonal projection of B onto the subspace on this span of AX, right? This is the x which I want to know. This is the x. So the x which minimizes this is B's projection on AX. Therefore, B minus AX, where x is my final answer, B minus AX is perpendicular to AX, right? Let me write it as x tilde to signify that this is one particular point, and this, however, is an entire space. So B minus AX is perpendicular to AX. That's the kind of x that I want to find. Right? This is like satisfied for all x, right? So I'm just trying to write another way. So B minus AX tilde, the AX prime, inner product with AX is equals to 0 for all x, for all x. So let me just bring the transpose here. It becomes A transpose B minus AX prime x is equals to 0 for all x, which means that this, if this inner product is 0 for all x, well, it should mean that this is the one which is 0. So A transpose B minus A transpose AX prime is equals to 0. Again, coming to the normal equations, that is A transpose AX is equal to A transpose B. A transpose AX is equals to A transpose B. That's the normal equation. Well, anyway, we are going to talk next about the condition of this problem, like how well is this problem posed, right? So this is the problem that we are trying to solve. In theory, A transpose AX is equals to A transpose B. Or let's give it a geometric perspective. Let's say this was my hyperplane, this is AX and this is B. And now I project this to a point given by P times B. P is just a projection matrix on AX. So this is my point, PB. So what I want to find is, if I change B a little bit, how does my output change? That's the question. So with respect to changes in B, how does my PB change? So the condition number is the absolute condition, no, the absolute condition number, as I defined it as, f of well, I defined the condition number as the change in output depending on the change in input, right? And we would define it, the relative condition number, as norm of x divided by the norm of fx times the f prime of x, norm of f prime of x, given that that is differentiable. This is the relative condition number, isn't it? So obviously, this is how my f looks. It takes b as an input and returns pb. This is my f. F prime is p because it's a linear function. It's directly differentiable. So my relative condition number becomes norm of b divided by norm of pb times P. Right? Now, norm of P divided by the norm of PB. Well, the norm of PB divided by the norm of P, in the two norm, this becomes the cosine of this angle. Let me call it alpha. So this becomes the norm of P divided by the cosine of this angle alpha. What this means, forget about that. Forget about the formula. I don't care about the formula myself. That's why I did not remember it. What it means is, if my angle was smaller, that means my B was very close to my AX. A little change in B does not change my PB very much. It does not change the projection very much. Instead, if my B was perpendicular, let's say, or almost perpendicular to AX, a little change in B would change my PB quite a lot. So if my angle was smaller, let's say my alpha was smaller, my cos alpha would almost be 1. In that case, my condition number is the norm of the projection matrix. If my alpha was bigger, that means this denominator was closer to 0 and my condition number would be larger. So that's the point. If my B was smaller to the subspace, the span of AX, my model is better. My model is very close to the real number. That means it can do a better condition number. It is a better condition problem, so to speak. Now, this is what the textbook says about the condition number of the problem. Let me write it. The condition number of this problem with respect to perturbations in B is equals to kappa 2 of A divided by cos of the alpha. With respect to A, this becomes kappa 2 of A plus kappa 2A square tan of that alpha. So as you can see, if an alpha was close to, let's say, 90 degrees, both of these numbers are huge, ill-conditioned. If my alpha was close to, let's say, 0, this is a smaller number, this is a smaller number, so it's a well-conditioned problem, relatively. It can be derived by writing x as phi of b. Phi is just another function. I'm going to write in terms of b, which is A transpose A inverse A transpose b. Like I'm just solving the normal equations. Now I differentiate with respect to b. The relative condition number. The relative condition number becomes differentiation of this and then multiplying and dividing by the input and the output numbers correspondingly. That's what my condition number is, kappa is. Kappa is norm of phi prime with respect to b divided by x, which is the output, and b, which is the input. Substitute phi prime from there, putting this just as it is. X is equals to, I write it in such a manner. Phi prime, I put phi prime as A transpose A inverse A transpose. This is my phi prime. I divide it by the x norm and I multiply with the b norm. Just copying the definition, just following, just doing steps, right? Never mind, just remember this, forget about it. Okay. Just technical steps, go to the FL hard if you want to see how it is done. I don't understand this actually myself, so is this one thing that I wanted to mention, which I forgot, was why don't we solve the normal equations directly? For example, why don't we do A transpose A x is equals to A transpose B? Why don't we just, write A transpose B as, let's say, capital B, and A transpose A is, let's say, small a. So I just write Ax equals to B and solve whatever linear solvers do I have. Well, why we do not do that is because of this A transpose A. Let me give you an intuition why we don't do this. For example, I have a matrix A. It's a big matrix, 1000 by 1000 rows and let's say 10 columns, whatever. I do A transpose A. That means I'm multiplying all of those 1000 rows with themselves in the transpose manner. So if there are some errors in a particular row, in a particular column, I am multiplying those errors again with itself. So what I'm trying to emphasize, what I'm trying to say is, doing an A transpose A compounds the error in a matrix. And we'll look at that. We'll look at why this is true. So let me see the condition number of A transpose A. What I want to prove is the condition number of A transpose A is the condition number of A squared. And it makes sense too a little bit, you know, A transpose A squared, they are at least in the same dimensions error wise. So let me write kappa 2, and this definition is in the norm 2. This definition is in the 2 norm actually, and that's like a very widely used norm. So the 2 norm kappa is equals to the maximum of Ax divided by the minimum of Ax, right? That's how we define the 2 norm. I'm squaring this, so I'm going to square these. Norm square is equals to x transpose A transpose Ax max divided by min x transpose A transpose Ax. I'm going to switch around a bit again. This becomes max of A transpose Ax times x, inner product, divided by min of A transpose Ax and x. Right? So now for this normal matrix, A transpose A is a symmetric normal Hermitian matrix. I write this as the lambda max of A transpose A divided by the lambda min of A transpose A, which is nothing but the kappa 2 of A transpose A. So what I proved is the square of norm of A, square of condition number of A is the condition number of A transpose A. So if I were to directly solve this A transpose A, I am going to square the condition number of my problem. So even if my condition number was, let's say, 10, if I were to solve the direct normal equation, my condition number becomes 100, which is like a big deal. Squaring the condition number, that's why we never do A transpose A. So how would you solve this? Well, that's when we have this idea. We don't want to do A transpose A. We do not want to construct the matrix A transpose A at all. Because when we construct A transpose A, this is what happens. For example, this was A. Then this was A transpose. If this column, if column 1 had, let's say, epsilon error here, epsilon error here, epsilon error here, epsilon error here, by multiplying, I'm going to compound all of these errors, which is not something that I am very interested in doing. So, how would one solve this? One takes this idea, the orthogonal projection. If somehow I'm able to find vectors which have the same span as A, and those, if I'm able to find a matrix which has the same span as A. So for example, this is what I'm saying. Span of A is equals to span of Q. If I'm going to find a matrix Q in such a manner, with also the condition that Q transpose Q is identity, that is, it's an orthonormal matrix. If I'm able to find a Q which is an orthonormal matrix which has the same span as A, I can very easily project B onto this subspace AX. That will be the discussion in the next video.